Okay, so before we move to the next proposition or theorems, let's really compute what this cross ratio is by the definition. And with this computation, it can convince us this is really the case, not just proved by the properties. So let's compute T of TZ, TZ2, TZ3, and TZ4. To cover all possibilities, we assume here Z2, Z3, and Z4 are non-infinity. They are all complex numbers. One of them is infinity. You actually take the limit. Okay, so let's see what it is. So by the definition, it is Tz minus Tz3, Tz minus Tz4 over Tz2 minus Tz3, Tz2 minus Tz4, right? And here T is a Mobius transformation. Let's assume T is a AZ plus B over CZ plus D. Right? So this is the definition. We are going to compute top and bottom separately, but the bottom is actually the evaluation of the top at Z equal to Z2. So let's just compute the numerator first. From the computation of the numerator, we can see the denominator. Okay, Tz, Tz3, Tz4, let's apply it. So it's Tz, Tz3, Tz, Tz4. Right? Just apply the formula of Tz. And then we're going to multiply top and bottom by Cz plus D, Cz3 plus D, Cz4 plus D. So Cz plus D, Cz3 plus D, Cz4 plus D. I want to cancel the denominator. All right. Okay, after we cancel denominator, let's see that here we have, after we cancel CZD, we have CD3 plus D, CD4 plus D. But actually this CZ4 plus D, it will appear in the first and second term. So we will keep it as a factor. So it's AZ plus B times CZ3 plus D. And AZ3 plus B times CZ plus D. And this difference times CZ4 plus D, right? Just first to use these two terms to this product to multiply those two, this difference, and then multiply CZ4 plus D. Similarly, we will have AZ plus B, CZ4 plus D minus AZ4 plus B, CZ plus D, and CZ3 over D. Right? So you just use these two factors to simplify, to cancel the denominator. Well, after that, just plain computation. So AZ, ACZZ3, ADZ, BCZ3, and BD. This is the first four terms, a minus ACZZ3, ADZ3, and BCZ plus BD. It's a difference, and then CZ4 plus D. Okay, it's a little bit long, but it's okay. So here is a ACZZ4 plus ADZ, yes, plus BCZ4 plus BD minus ACZZ4 plus ADZ4 plus BCZ plus BD, CZ3 plus D. Well, I hope I don't make mistake. So here, ACZZ3, they're cancelled. BD, they are cancelled. Similarly, ACZZ4, they are cancelled. BD are cancelled. So what we have in the bracket is ADZ plus BCZ3, these two terms, minus ADZ3 minus BCZ, and CZ4 plus D, and denominator ADZ plus BCZ4 minus ADZ4 minus BCZ, CZ3 plus D. Right? Okay, let's combine them. So ADZ minus BCZ. So it's AD minus BC Z. Here is plus BC minus AD Z3. And similarly, AD minus BCZ, AD minus BCZ, plus BC minus ADZ4. Right? And you can see BC minus AD, AD minus BC. You change it to be minus sign. This is AD minus BC. You can factor it. So you will get AD minus BC, Z minus Z3, Z minus Z3 in order to factor it. CZ4 plus D. AD minus BC. Of course, here it will be Z minus Z4. CZ3 plus D. Okay, remember T is a Mobius transformation. AD minus BC not 0, so you cancel them. So eventually, what do you get? This is the numerator. Well, the computation is long, but there's no difficult, just computation, fractional computation. Okay, so this is a numerator, and when you want to get the denominator, you just replace z by z2, so the denominator will be the same thing. So now let's similarly. Let's simplify it. This big ratio becomes this one. This is numerator, and big denominator, z2 minus z3, cz4 plus d. This is coefficient, so it doesn't change. z2 minus z4, cz3 plus d. It doesn't matter you apply z or z2. And you see that even though here you cannot cancel them, but you can cancel this part and this part from big top and big bottom. So eventually you will get a z minus z3, z minus z4 over z2 minus z3, z2 minus z4. This is the proof or the computation. It's not a proof at all. It's just plain computation. Right? So it's very long. You just understand the definition and do it step by step. You can get it. But you can also see the the smart proof based on the property. But anyway, you should be able to apply the basic definition, or you can apply the basic property. Either works. So okay, so this is let me move it down. Whole computation. Okay, so after we finish this, well, this just computation, let's move to the next one. Next one, we say that if in geometry, three points have two possibilities, can be in a line or determine a circle. 3 points can be in one line or collinear or determine a circle. And in C infinity, a straight line is also, well, a straight line in C is also a circle. A straight line in C is also a circle in C infinity. In C infinity. So here we can, by this viewpoint, we can say that in C infinity, any 3 points will uniquely determine a circle. Okay, any 3 point will uniquely determine a circle. So that's a fact. But what about 4 points? 4 points may not be in a circle, right? 4 point, you can have a triangle and a point inside, or a point outside, possibly outside. Okay, so we want to determine what happened. What happens if there are 4 points in C infinity? If there are 4 points in C infinity, what may happen? Will they lie in a circle or not? Okay. So that's the proposition 3.10. Let Z1, Z2, Z3, Z4 be 4 distinct points in C infinity. Then we can form the cross ratio. The cross ratio is an image of Z1 under the unique Mobius transformation. This is a complex number. It is a real number if and only if all 4 points lie on a circle. Lie on a circle. Okay? So when can we say 4 points lie on a circle in C infinity? We will check the cross ratio. If the cross ratio give us a real number, then it is on a circle. Okay, it's very cool. Okay, now let's see how and what happens. Cross ratio. Let's define this cross ratio. Let S from C infinity to C infinity be defined by S of Z equal to the cross ratio Z, Z2, Z3, and Z4. Z2, Z3, and Z4. And we want the value to be real. We want the value to be real. Then we can check the pre-image of real values, of real numbers, as inverse of R. It is the set of Z such that the cross ratio is real, right? It's a definition. The cross ratio is real. And we will prove, we will show that S inverse of R or R infinity, because Z4 is mapped to infinity, so we consider the infinity. S inverse of R infinity is a circle. We're going to show it is a circle. Actually, we do not just show this is a circle. We show that R infinity, the image we will in fact show that the image of R infinity under any Mobius transformation is a circle. Here, circle means either circle or a line in C, but in C infinity, they are both called circle. Okay, so here, this condition, this requirement just needs the image under S inverse to be a circle, but we do not just show the special case, we show the general case. For whatever Mobius transformation, R infinity will have image a circle. Okay, so this is a stronger result. Okay, now let's see. Let S of Z be AZ plus B, CZ plus D. See here, we're going to always start from the definition AZB, CZD. And remember that we need to map the we need to map what? We need to map study the real number. So for X in R, if we have, let me see what we need. X in R S mapped. S mapped whatever point to a real number. S mapped whatever point to a real number. Yes, the image is a real number. Right? S mapped, yes. Okay. It is a real number. What is the property of a real number in the complex world? Real number means conjugate is itself. SW is equal to for C. SW is equal to the complex conjugate of SW. Okay? Okay, so complex conjugate, let's see, SW, AW plus B, CW plus D. Its complex conjugate, A bar W bar plus B bar over C bar W bar plus D bar. A fraction is equal to another fraction. Right? Okay, well, do the cross multiplication. Cross multiplication AW plus B, C bar W bar plus D bar is equal to A bar W bar plus B bar, C bar plus D bar, CW plus D. And do the multiplication and move all the terms to the right side, left side, we will get the following one. AC bar minus A bar C times the norm of W squared plus AD minus BC times W and plus BC bar minus DA bar times W bar and plus BD minus B bar. Let me see this one. This is not. It is a BD bar and B bar D is equal to 0. Okay. You see here, this one, this S of Z, we didn't use the Mobius transformation. We just say use the same name. So this is still a Mobius transformation. But this Mobius transformation is not the, it's not this Mobius. It's actually what? X is a real number. So we let W be S inverse of X. So under arbitrary Mobius transformation, we mean under this S inverse. Okay? S inverse X W. W, we will prove it satisfies the property. So I feel I didn't make this clear, so I try to understand, add this part. So we are going to show that this W, the image of this real number under such Mobius transformation, will be in a circle. On the circle, not in the circle, on the circle. Okay? Okay, so what's next? Okay, now we have this quadratic equation, quadratic condition. Quadratic, you have to really get a non-zero leading term. So two cases. Case 1, if this is 0, this one is 0, then AC bar is A bar C. It is AC bar conjugate. So it means AC is real. Case 1, when AC bar, not AC, AC bar is real. When AC bar is real, the first term disappears. You only have the second term, second, third, and the final term. Well, let's see. This term, I think we need, here have a bar, B bar D. Yes, sorry, I missed 2 bar. AD bar, B bar C. Okay, now let's see. If you check this AD bar minus B bar CW, then the second term is actually the negative AD bar minus B bar C W conjugate. This is the second term. Right? Or you just use subtraction. This term comes from here, and this term comes from here. So remember that when you have a Z and minus its complex conjugate, it becomes a pure imaginary number. Pure imaginary number. Okay? Okay, so this one is the same thing. It's a BD bar minus d bar conjugate. This is also a pure imaginary number, a pure imaginary number. So actually here, the last three terms will give us a pure imaginary number. It is equal to 0. It means the coefficient is 0. The imaginary part is 0. Okay, so here we get the AD bar minus B bar CW plus BC bar minus DA bar W and plus BD bar minus B bar D is an imaginary number. Is a pure imaginary number. Pure imaginary number. You add z with z bar, you get the real number. You do the subtraction between z and z bar, you get the pure imaginary. Okay, and then we just try the pure imaginary number equal to 0 if and only if the y is equal to 0, right? So we try to get the imaginary part. How do we get the imaginary part? We just have, you see, how do we get this y? We multiply it by I, we will get the, we will cancel this sum. We will cancel I, we will get the negative sign, right? We multiply two sides by I, and you will have a negative sign, and that's the reason you get the imaginary part of alpha times W minus beta equal to 0, where you have alpha equal to 2 AD bar minus B bar C, and beta equal to I BD bar minus B bar D. Okay, so that's how we study this, how we come up with this imaginary part, and this beta is real. Beta is a real number. In this condition, why it becomes a minus sign? Why it becomes a minus sign? The reason is that this beta, check here, the beta is IBD bar minus B bar D, and BD bar minus B bar D is a pure imaginary number, like a 2yi, and then you multiply it by the I, you will get negative sign. You will have a negative sign, right? You have a negative sign. That is the reason there is certain negative sign there. And the first part, you don't, in the textbook, they say multiply this equation. This is called a 3.11. Multiply 3.11 by I. If you multiply it by I, you see here this difference we mentioned, it is already a pure imaginary number. So you will get AD bar minus BCI, B bar C, I times W minus AD bar minus B bar C, W complex conjugate. It's a pure imaginary number. We multiply it by I, we do have the imaginary part of this alpha W. We do have this part. This imaginary part is related to the product with I. So in this part, once we use imaginary part, we don't see the I. If you don't use the imaginary part, you have to get certain I symbols insert in this place or in that place. Okay, so try to write it down and make it clear. Try to write it down and make it clear. For example, if you call this as a if you call this as a we use alpha, beta, W, Z. Let's use Z. If you call this Z, this is minus Z bar. So it is imaginary part, twice of imaginary part of Z times I. And then you times I again, you will get a negative 2 imaginary part of Z. This is the first part. And the second part, you get Z minus Z bar and plus I times BD bar minus B bar D. And this one, we consider it as negative beta. We consider it as a beta. It's equal to 0. So you have negative 2 imaginary part of a Z plus beta is equal to 0. So this minus sign. Twice of Z. How do you get this 2? 2 is in the definition of here. Alpha is 2 times of it. So it's an imaginary part of a 2Z minus beta. Beta is a real number, so you don't have it. So there's some computation. It's not difficult, but sometimes it's just confusing. How do we get a plus sign? How do we get a minus sign? Stuff like this. Okay? Okay, so from here we get the imaginary part is equal to 0, and this determines a real line. Okay, and so W lies on the line determined. Let's put a 3 star, determined by 3 stars. Okay, so this is a case 1. In the case 1, we have a straight line because the quadratic equation becomes a linear equation. Linear equation will have a straight line. Now let's talk about case 2. Case 2 contains even more computations. Well, case 2, the leading coefficient is not equal to 0. Well, if it's not equal to 0, let's divide the quadratic equation by the leading coefficient. I want the leading coefficient, number 1. So we have AD bar minus B bar C over AC bar minus A bar C. W and plus BC bar minus DA bar over AC bar minus A bar C. W bar and plus BD bar minus B bar D over AC bar minus A bar C equal to 0. Okay, we do have a quadratic equation. And the quadratic equation, we're going to complete a square. So I'm going to move this term to the right side. And be careful, this term is a real number. So here, this is a real. Why it is a real number? Remember, the numerator is a pure imaginary. Denominator, you can see it's also a pure imaginary. Pure imaginary over pure imaginary, I canceled, so this is a real number. So we're going to move it to the right side. And the left side, if you check that, this number and this coefficient, these two coefficients are conjugate to each other. So you see AD bar minus B bar C, AC bar minus A bar C. If we put complex conjugate, we'll have a bar d minus b c bar, a bar c minus a c bar. They're different, but you exchange the numerator and denominator, and not exchange. You multiply top and bottom by -1. You see. So this is a pair of a complex conjugate numbers. Okay, so the following we are going to simplify the notation. Let gamma be this number. So BC bar minus DA bar over AC bar minus A bar C. This is gamma. This number we're going to move to the right side. It becomes minus, so the delta is negative BD bar minus B. Okay, this is negative because you move to the right. I want a plus delta, not a minus delta. Okay, so with this simplification, what we have in this lecture is just full of computation. So we'll get W modular square plus, this is gamma, this will be gamma bar W plus gamma W bar. Complete square in the complex number system, it's like this. You add gamma modular square. Okay, and then these two, it is actually, it's actually like this, because this one is W plus gamma times W bar plus gamma bar. If you check it, it's exactly this. And this right side, let's compute this right side, because left side is 0, is a positive non-negative number. It's modular square. It's a real and non-negative. And I want to know this right side is also positive. Okay, so so we're going to compute this. Gamma modular square is gamma times gamma bar. This is gamma bar. So it's AD bar minus BC bar over AC bar minus A bar C, and times this. BC bar minus DA bar AC bar minus A bar C. The denominator is the same. And delta is this, minus BD bar minus B bar D, AC bar minus A bar C. Okay, so I'm going to find the common denominator. So we will have AC bar minus A bar C, AC bar minus A bar C. It's not interesting at all about computation, but we have to convince us. So the denominator will be the same, AC bar minus A bar C square. The numerator, remember, then check the numerator. It's A, B, C, D, A, B, C, D. So C bar, D bar, A times this one, it's modulus A square, modulus D square. You see, A bar, D bar, D. And this one is minus modulus B square, modulus C square. And this one is plus A, B, C, D, but A bar and B bar. That's product of the first 4 terms, and minus the product of the last 4 terms, A, B, C, D. So A, B, C, D, you have C bar, D bar, C bar, D bar. This one, and minus A, B, C, D, A, B, C, D. It's A bar, D bar, A bar, D bar. And this one is minus A, B, C, D. It's a C bar, B bar. And this one is plus A, B, C, D, but it's A bar and B bar. It's a product of these 2 terms. And the whole thing after the subtraction, you will get AC prime minus AC bar minus A bar C squared. Wow, what do we have? We have this term cancelled with this term cancelled with this. So we will have A bar C, A bar B C D bar plus AB bar C bar D. These two terms positive and these two terms negative. And AC bar minus AC square. Okay, now it's about the factorization. It's about factorization. And be careful, keep in mind, this without a square, it's a pure imaginary number. With a square, it's a negative number. Okay, with a square, it becomes a negative number. This is a negative. So if we don't want a negative number, we need to factor out the negative sign. So after we factor out the negative sign, we will get AC bar minus A bar C times A bar C minus AC bar. We exchange the position to get a negative sign. With the negative sign, you also change the numerator. A bar D bar BC minus AD B bar C bar and plus BC B bar B modular square C modular square. Okay, so the numerator, if you check that, you can see the AD together, BC together, it is AD minus BC modulus square. It is AD minus BC, A bar D bar minus B bar C bar. You do the multiplication, it's a numerator. And denominator, it's the first term times the conjugate. Okay, so it's AC bar minus A bar C modulus square. Okay, so write in one stuff. It is also a positive real number. Well, once it's positive, of course it's real. Or it's not 0 because AD minus BC is not 0, so this one is never 0, it's greater than 0. So what do we get? We get W plus delta is equal to the modulus AD minus BC over AC bar minus A bar C is a circle. Is a circle. Okay, so that's it. That is the whole proof. Okay, so let's stop here. We already have a lot of computation in this short video. This is a 40 minutes video, but we just keep computing. There's no tricks at all, just computation. And sometimes we use letters to simplify the writing, but still you need certain detailed computation. And plus the observation, you always keep in mind, if you add a pair of conjugate numbers, it's real. If you subtract a pair of conjugate number, it's pure imaginary. All right, so that's the only stuff. So maybe in some places I was not in the right order or the proper order, but just go over it and make sure you understand what I'm writing. Okay, so see, let's start here. In the first computation, we try to really compute the cross ratio of a TZ, TZ2, TZ3, TZ4. The computation is based on the definition. Okay, and we compute the numerator. We quickly compute the denominator and simplify it. So that's just a attachment for the last video. And then we observe that 3 points always lie in a circle in C infinity. Then we want to study the property for 4 points in C infinity. The proposition says 4 points in a circle if and only if the cross ratio is a real number. So we prove this. By prove this, we do not directly prove it. We just show that the real number is mapped to a circle. the real number is mapped to a circle. So this is arbitrary Mobius transformation. This is W. We are going to determine the property of a W. So S inverse is S inverse of X is W. So S of W is X, and SW is a real number. So the complex conjugate is equal to itself. So we get this quadratic equation. And then the rest of the computation is the analysis of the solution of this quadratic equation. Right? Is the solution of this quadratic equation. Okay, so we have the proof. The case 1, when this quadratic equation degenerate to a linear equation, you will get this part, and this linear equation give us a straight line. A linear equation give us a straight line. The imaginary part is 0. Actually, this is a parameter t. This give us the parameter t. Okay, be careful. This one is actually the determination of the parameter, real parameter. The real parameter. It only depends on one quantity. Okay, and second part, if the quadratic equation is really a quadratic equation which is complete square and find the radius. This is a complete square process. We make sure that the radius is positive. So we have such a computation. So I hope at this moment let me see here. Yeah, I hope at this moment the proof or the computation, the rhythm behind the computation is clear. Okay, so we finish this video and we finish this lecture. If I was not clear at any point, just send me email. Okay, I'm happy to answer questions. Thank you.